In 1964, two brilliant yet totally unlucky astronomers in New Jersey had a massive problem. They had built the most sensitive antenna on Earth, and it was picking up a relentless, annoying, inescapable hum. They tried everything. They aimed it at New York City, thinking it was noise pollution. No change. They cleaned the antenna from top to bottom, thinking it was a buildup of biological contaminants. They even suspected their equipment was too hot, but the hiss would just not stop, which was the luckiest failure in history, because they weren't cleaning up equipment problems. They were trying to scrub away the faint 13.8 billion-year-old echo of the Big Bang itself. This all took place at Bell Labs in New Jersey. The two main characters were Penzias and Robert Wilson. Their instrument was the Holmdel horn antenna. It was giant, it was sensitive, and it was supposed to be silent. They were trying to measure the very faint radio signals reflecting off our atmosphere. But every time they pointed the antenna at a blank patch of sky, they heard it. A constant, unyielding, low-level hiss. It was like watching a television with bad reception, only the sound was isotropic. This means it was coming from all directions at once, ruling out any local sources like the sun or New York City. It was also always the exact same intensity. This was the beginning of their 6-month war against nothing. They started by cooling the receiver with liquid helium, thinking the noise was the equipment itself overheating. No change. They checked for nearby military signals or radar interference. Negative. The mystery got so frustrating, they resorted to the last great solution in the scientist handbook, cleaning. They spent weeks meticulously removing nests and residue from the throat of the giant horn. Still nothing. The hiss was 100 times stronger than it should have been. They had eliminated everything. Every known source of noise, every possible contaminant, except for the universe itself. But if this was the universe, why was it still so hot? The reason Penzias and Wilson's antenna was so hot is simple. The Big Bang theory required that the universe must have started scorching hot and incredibly dense. But the early universe wasn't a fireball. It was more like a thick orange fog. Imagine trying to see on a day where the smog is so thick you can't see your hand in front of your face. That was the entire universe for the first 380,000 years, and it expanded the whole time, simply coasting on the momentum of its initial creation. At this time, the temperature was a blistering 3,000 Kelvin. Nothing looked like the universe we know. There were no stars, no galaxies, no atoms. It was a sea of charged particles, protons, neutrons, and free electrons. And there were photons, particles of light, being created all the time. But here's the problem. Light hates charged particles. Those free electrons were everywhere, acting like a constantly moving cosmic crowd. Every time a photon tried to fly, it would bounce off an electron almost immediately. Light couldn't travel more than a few centimeters before being smacked down. This constant scattering made the universe entirely opaque. The light was permanently trapped. But after 380,000 years, the universe expanded just enough to cool down. As the temperature dropped below 3,000 Kelvin, the cooling hit a specific critical threshold. The free electrons and protons finally said, "We give up." They combined to form the first neutral hydrogen atoms. This event is called recombination, which is a very nerdy word for the universe finally decided to clear its throat. The charged particles were gone. The cosmic crowd vanished. The universe was ready to be seen for the very first time. But what happened to all the trapped light when the fog lifted? When the first neutral hydrogen atoms formed, the moment was beautiful. The particles of light and matter were now free from each other. The fog was gone. All of those trapped photons that had been bouncing around for 380,000 years were suddenly free to fly. This flash of freedom is what we call the surface of last scattering. This is why we can never truly see the start of the universe. We can only see the picture of the final wall of fog. This is the cosmic microwave background, or CMB. It is a map of the entire sky showing the temperature of that first light. Penzias and Wilson found that this light had been traveling for 13.8 billion years to reach their antenna. But there was one final, massive paradox. The light left that surface when the universe was 3,000 Kelvin, about 5,000 degrees Fahrenheit. But Penzias and Wilson didn't measure 3,000 Kelvin. They measured 3 Kelvin. That's 3 degrees above absolute zero. That's cold. Why did the heat drop so drastically over the journey? The answer is the second most important physics concept in this video, redshift. The light left the surface of last scattering as visible, searing hot light, but it traveled across an expanding universe. As space itself stretched, the light waves stretched with it. Think of it like drawing a wavy line on a rubber sheet and then pulling the sheet apart. The waves get longer, and the longer a light wave is, the cooler its energy is. Redshift took the Big Bang's light and turned it from hot, visible light all the way down to cool, harmless microwaves. So, the CMB proved the Big Bang, solved the mystery, and won a Nobel Prize. End of story, right? Not quite, because the actual map of the CMB created a problem no one saw coming. At the time Penzias and Wilson were scraping their antenna, they had no idea they were sitting on the biggest discovery in physics. They didn't even know what the hiss was. That part belongs to a rival team at Princeton University, led by physicist Robert Dicke. Dicke's team had been building their own antenna, working on the theory that if the Big Bang was real, there had to be this cosmic afterglow. The two groups connected, and the conversation was legendary. Penzias explained the noise they couldn't get rid of. Dicke's face went completely blank. He reportedly turned to his team and said, "Well, boys, we've been scooped." The phrase "scooped" meant the rival team found proof first, winning the discovery. Penzias and Wilson were awarded the Nobel Prize in Physics in 1978 for the measurement of CMB, while Dicke's team published the paper explaining the theory behind it. Case closed. Big Bang confirmed, but the real work was just starting. Once the universe was confirmed to be a massive radio emitter, scientists wanted to see the full map. They launched the COBE, Cosmic Background Explorer satellite, to map the entire sky. The initial results confirmed the discovery. The universe was bathed in a uniform glow of 2.725 Kelvin, and that was the problem. The initial map was too perfect. It was almost perfectly smooth. The slight variations in temperature were so tiny, they were initially called dipoles. The map was essentially uniform, showing no difference in temperature, no matter where you looked. Now, think about the universe today. It's lumpy. It's full of massive clumps of stuff, like galaxies, superclusters, and you. And lumpy things come from lumpy beginnings. If the universe started out perfectly smooth, with no difference in density or temperature, gravity wouldn't have had enough time to pull matter together into stars and galaxies in 13.8 billion years. It would have needed a head start, a few tiny bumps in the road to act as seeds for the galaxies we see today. The Big Bang was proven to be real, but the resulting map implied a universe that shouldn't exist. The universe was a perfectly smooth, boring baby. So how did it grow up to be a lumpy, star-filled mess that we see today? The problem of the smooth universe baffled scientists for 2 decades. It meant the Big Bang was true, but the entire history of creation shouldn't have been possible. The solution, as always, was found not by building a new antenna, but building a better one. In the 1990s and 2000s, NASA launched the COBE WMAP and then the Planck satellites. These missions were designed to measure the CMB with a level of precision that was frankly absurd, and they found something incredible. The universe wasn't perfectly smooth. The map of the CMB was covered in tiny, tiny ripples. To understand those ripples, imagine a thermometer stuck in the sky. Every spot on the map reads 2.725 degrees Kelvin. These missions found tiny spots that read 2.2751 Kelvin and tiny spots that read 2.7249 Kelvin. These slight differences in temperature, about 1 part in 100,000, were the seeds. They represented tiny differences in how matter was spread out. They were the imperfections that gravity needed. Over 13.8 billion years, those tiny seeds grew into galaxies, clusters, and the entire cosmic web. So, back to our original question, did we really see the Big Bang? No. We just saw the universal wall of fog 380,000 years after the fog lifted, but the cosmic microwave background is more than just an echo. It's a baby picture of the universe. It's a map of the seeds of every single star and planet that will ever exist. It's a final piece of evidence proving that even the most chaotic, fiery beginnings start with a tiny, beautiful, perfectly placed ripple.